Have you ever wondered how universal function generators work? How do circuits generate any arbitrary function with an input voltage? Um, the way that this is done is there are multiple principles, one using an analog function generator and another using a digital function generator. So today I'm going to show both of these concepts, and hopefully you can apply this into your own circuits. So first of all, I'm going to show a way to generate any function using the clipping on comparators. Um, the clipping on amplifiers. So what I have here is a series of amplifiers where the gain of a input signal passing through here is multiplied by some factor. So here it's multiplied by um, 2, and then this is multiplied by 2 again. And then this is multiplied by 2 and 2 and 2 and 2 and so on. And normally, if we summed up all of these voltages, right, what you end up with is a constant line. So a constant function with regards to the input voltage. However, because the amplifiers have a rail voltage that they can only go up to, if any of these amplifiers clip, they will actually change the slope of the line at a particular cutoff voltage. So I'll first demonstrate the result of this. So here I have the input, which is just a linear voltage that goes from 0 volts to 1 volts in 1 second. And then let's look at the output. So as you can see, the output is basically an approximate log function. It's a piecewise function because it has a different slope at every targeted piece. So how does this actually work? So what happens is, when the voltage is low, let's say 0.1 volts, for example, none of the amplifiers are going to be cut off. So for example, this is 0.1 volts, it can output 0.1, multiplied by 2, so it can output 0.2, this one can output 0.4, 0.6, 0.8, etc., etc., etc. And therefore, as the voltage increases from 0 to 0.1 volts, all of these amplifiers are contributing to the voltage increase, the rate of change of the voltage. So, that's why the slope is the steepest when the voltage is low. 0.1 is just the arbitrary value that I picked. In reality, it's not. But yeah, basically, the more stages that contribute to an increase in the voltage, the steeper the line would be. However, what happens if the voltage starts getting a little bit too big? If the voltage starts getting a little bit too big, the voltages at the ends of these amplifiers, because they're fed in from the previous stage, the voltages will be multiplied by all of the previous stages, and it becomes so high that the later stages can no longer amplify, so it ends up clipping the voltage off. And so what happens is, instead of outputting, let's say this stage, instead of outputting the previous stage multiplied by 2, it'll output the output VCC, which is constant voltage. So what happens there is, if the input voltage is too big, the later stages clip and they no longer contribute to the rate of change. They just output a constant voltage. So that's why you see that as the voltage has increased, the later stages will have a lower rate of change. Will have basically a slope that is smaller, because less and less of the later stages can contribute to the slope as the voltage increases in the input. So basically, by toggling the resistances on these amplifier stages, you can change the rate at which they start clipping, and therefore you can start changing the shape of the graph. Another thing to note is that why are these stages cascaded like this? Why is the input not just fed individually into these stages, and then um, have the gain adjusted accordingly. The reason is because this is a continuous function. So we don't want, for example, at some cutoff, the voltage to be jumping around. So for example, at this cutoff, we don't want the voltage to suddenly jump to down here. So therefore, uh, every change is successive in each stage. So that's how you get this sort of continuous voltage curve. When I was playing around with this, so first I discovered the circuit through So first, I discovered the circuit through analyzing log amps because this is a known piecewise function to approximate logs. And you can see why. It's because the rate of change is proportional to the current voltage, right? It's the higher the output voltage, um, the more stages are in cutoff. In saturation. So therefore, um, the more stages the stages that don't contribute to the slope anymore. And that's just the inverse of exponential relationship where the rate of change is proportional to the current output value. So next thing is, by changing these amplifiers, we can't actually get the gain to increase again. And we also can't get the gain to decrease. We can't get the voltage to drop. So obviously that's not going to be a very good universal function generator if we just had it like this. But I figured out there's actually ways to do this. So for example, if you actually look at what's happening within any particular gain stage, what's happening is it's essentially running a minimum function, right? So it's basically calling the min math function, and the two input values are the rail voltage and the output amplified voltage. So if the absolute rail voltage is lower than the intended amplified voltage, then it can only output the rail. So therefore, it's basically a mathematical min function. However, we can add stages in here that are basically the opposite, the mathematically max function. So here I have an example of this. This is basically two diodes facing each other, and you have the two inputs on the either side of the diode. And because diodes reverse bias in one direction and only forward bias in another direction, in the middle will only be the larger of the two voltages. So this is basically a max function. So I added this into an experimental circuit that I modified, which has a lot of gain stages, but has one of these sort of max voltage functions. And also, I have uh, a negative gain stage as well over here. So, this is the negative gain stage. So all of these other ones are plus, and then this is a minus. So if you look at the output, you can see that, let me just show you the output. You can see that I've actually created the characteristics required for basically any function to be created. This dip here is created by this negative gain stage over here. And over here as well. So these are two negative gain stages creating this dip. And then you can see that the slope actually increased again. And this is caused by this stage. So this sort of max of the two voltages stage. And basically using these building blocks, you can cascade things in a way such that they add up, the voltages of all the stages sum up together to be any function. And so you can basically approximate any piecewise function using this concept. However, as you can probably tell, it's really hard to design a circuit like this because then you have to work out, you have to decompose the different gain stages and figure out how you design them so that it adds up exactly to some shape. And it's not trivial to figure that out. So this is why this sort of pure analog way to create universal function generators are really used in practice. So the other way to create a universal function generator is to use a digital to analog converter. So you can basically write code in your microcontroller that outputs binary voltage in different pins. So like, let's say you have a 4-pin output. You can output from basically 0 to 16 volts in that case, or 0 to 16, whatever voltage interval you want it to be. And then if we can convert those pins, those binary pins, to an analog voltage, then we can use that to create a universal function generator. So I have two ways that this could be done. The first is to use the binary weighted digital analog converter. So here I have 5 pins, right? And they either pull high or pull low. So they either output 0 volts or 1 volts. So this could be basically connected to a microcontroller that programmatically changes the binary representation of the voltage over time. And then to get the actual voltage back out, you essentially put this through a analog adder, but you have a 2x resistor on the binary output side for every bit that you want represented. So, for example, for the first bit, for the fifth bit, so the bit that is the largest in this case, I have 100 volts, 100 ohms in the resistance, and then 200, which represents the fourth bit, etc., etc. And what this actually does is it weights the voltage output at bit 5, so at the fifth pin of the microcontroller output. It gives more weight to this pin than the fourth pin. And how much more does it give? It gives twice as much weight because the resistance is halved. And so therefore, basically, what's going to happen is bit 1 is going to contribute 1/16 of the voltage that bit 5 contributes. Bit 2 is going to contribute 1/8, and then 1/4, and then 1/2. And this is basically a binary adder now, right? Because this represents exactly what binary values are for. For example, if you have 0, 0, 0, 1, that's just 1 times 1. And then if you have 0, 0, 1, 0, that's 2 times 1, etc., etc. 4 times 1, and 8 times 1, and 16 times 1. So that's exactly what this is doing. It's outputting basically a binary weighted voltage and summing it up and then amplifying it back out again. So I'll just demonstrate what this means, the result of this. So here I have a binary input 0, 0, 0, 1, which you can generate very easily in your microcontroller. And then the output here is summed. So only the first bit will contribute, right? These are not contributing. And this is basically divided by 16 and multiplied by 16 again. So the output here is 1 volt. You can see it's 999 millivolts, but yeah, that's close enough to 1 volt. And then if we added this as well, added this bit, you can see that the output is all of a sudden 3 volts, right? Because now both of these are contributing, and the second bit is twice the voltage of the first bit. It's the same voltage input from the pin, but because of the voltage divider created by the adder, it's going to be twice the voltage contribution of the first bit, and so on and so forth. So let's do something like I want to have the fifth bit have 1, and then let's say the third bit have 1, and then 0, 1. So what is this in terms of analog? This is 1 volt plus 4 volts, so that's 5 volts, and then plus 16 volts, so that should be 21 volts in the output. Let's see if we get that. And we do, so we get 20.99, so that's 21 volts. So yeah, this is obviously a very a decently implemented way to achieve digital to analog conversion. However, there are problems with this circuit. The biggest one is the more precision you want, which means the more bits you want to add, you got to keep doubling the resistor values. And this is a problem. For example, if I had a 32-bit output, my largest resistor has to be 2 to the power of 32 times larger than my smallest resistor. And obviously, that's going to be really hard to manufacture because the accuracy of the adder is going to be dependent on the accuracy of these resistors relative to each other as well. And you're not going to be able to manufacture a resistor that's 100 ohms and then another one that's like millions of ohms in the precision that's needed for a true binary adder. So instead, someone invented this really genius way to go about doing this addition, and it's called the R2R ladder digital to analog conversion. So how does this actually work? Let's just check that it works first of all. So I have the same 101010 here, and I should get a 21 volt in the output. Let's see if I get that. And I do. So it's a little bit over 21, so it's not super accurate, and I'll talk about why. But you can see the manufacturability of this is much better because the R2R ladder essentially is you put a resistance in series with in parallel with this main ladder that is 2 times the resistance of the resistors in series. So over here, all these resistors are 1K, and then you have these resistors 2K pointing down and towards the inputs, and then the last resistor has to be grounded. And so what's happening here, and this is a very, very genius setup. Like I'm not sure how someone came up with this, but it's just really smart. So what's actually going on, right, is let's say we ignore everything here and just look at the first bit. What's the voltage that this bit is contributing to this particular node? So it's basically a voltage divider, right? And what's happening is for this bit, it's going to basically have a 2K here and a 3K. Sorry about that. I just actually realized this needs to be 1K, which is why it was inaccurate before. So now you get 21 volts exactly because this is supposed to be 1K. So basically, if we look at the node contribution, it's 2K here, and then it's 2K in series to ground here. So therefore, this bit is this node is half of the voltage input by this bit. And so what about this node? So if we connected this node, and let's say bit 2 is just off right now and it's grounded, it's up in 0 volts, then what is the voltage at this node? Well, now we have half of bit 1 here going through the voltage divider, right? And the resistance here is 2K in series with 2K, in parallel with 2K, so therefore it's actually 1K. So this is a 1K resistor with a 1K resistor in series, so therefore it's a 2K resistor again, and the voltage input is half of bit 1, and so therefore this node, as contributed by this bit, is now 1/4. And if you extrapolate that, this will be 1/8 of this input, and this will be 1/16, and this will be 1/32 of this input. So basically, the closer the bit is towards the final output, the larger it contributes to the final voltage of the output. And every position that is closer, it actually contributes twice as much because of this 1K, 2K series parallel relationship. And when I was analyzing the circuit, so this part made sense, but the part that didn't make sense is how can we just add the voltages together? For example, this bit, right? It contributes 1/32 to this node, and this bit contributes 1/16 to this node, but we don't use an adder anyway. So how is it that these two voltages can just be added and summed in this node? And actually, the reason for that is because what's happening is they're averages. So when you have two voltages and they go through a voltage divider and there's a voltage output in the middle of the voltage divider with the two voltages at both ends, this is basically a voltage average, right? So essentially, because of the way it's set up, it's essentially averaging all of the contributions, but then end up multiplying by the number of contributions again. And this is actually the genius of the R2R ladder. Unfortunately, I can't show math on here, but when you work it out, that's exactly what's happening. And because of the easiness of cascading an extra stage, you can basically manufacture as long of a ladder as you want. So as many bits of on this DAC as you need, and you don't ever need to use resistors that are larger than 2K and smaller than 1K. This last part is just basically scaling it back out to the voltage level that we want. But you can basically simulate this using just a normal op-amp amplifier. Great, so this is the video. Hopefully, this is useful to somebody. Thank you very much.